Alright, so let's have a look at this one here. So first things first, let's do a free body diagram of this sucker. So got this bar, let's call this A. Got 2 kilonewtons acting here. We've got 4 kilonewtons acting here. And we have some support AY. Got some support AX, but we know that's 0 because there's no other horizontal forces. And we're going to have some moment A. So I'm not going to bother solving for what the moment is, because we're only looking at shear stress in this particular problem. So if we want to solve for what AY is, so the sum of the forces in y direction is equal to 0, equal to AY minus 2 kilonewtons minus 4 kilonewtons. Therefore, AY is equal to 6 kilonewtons. Simple enough. So if we draw a quick diagram of our variation of the shear load over the span, 6 drops to 2, drops to 4. So the load, V, at the point that we're looking at is 6 kilonewtons. So next thing we should probably do is go ahead and figure out what the I is for our cross section here. So we've got kind of shape. I'm just gonna 20, 70 millimeters. This is 50 millimeters. And that's also 20 millimeters. So if we want to figure out what the I is, the best thing to do would be to kind of break that up into 2 different segments. So go for these colors here, a green and a purple segment. So let's see here. First off, we need to find kind of we'll define our axes here. So let's put our actually let's define our axes on this one. So here X, Y, and Z in relation to this. So in relation to the cross section that we're looking at, we're looking at Y and Z. So we're trying to find the IZ here, the so about the Z-axis. To find the I for the overall section, we need to find out what its centroid is. We need to find out what the individual components of the I for those 2 subsections are. So for the green one, so its area, that's going to be 20 millimeters times 70 millimeters. That's 1400 millimeters squared. The Y bar, that'll be 20 millimeters plus 35 millimeters. 25 plus 70 divided by 2, measured from this base here. So that'll be 55 millimeters. And then the its individual I component, again, it's height cubed times base divided by 12. So 70 millimeters to the third times 20 millimeters divided by 12. That gives us 571,666 millimeters to the fourth. For the purple one, same idea, area, that is 50 millimeters times 20 millimeters, so 1,000 millimeters to the third. Its y bar measured from the base, 10 millimeters, and then its I component, 20 to the third times 50 divided by 12, so that'll be 33,333 millimeters to the fourth. So let's find the y bar for the entire thing. So again, our y bar is going to be equal to the sum of the area for each section, the area times the y bar for each section divided by the sum of the areas. So that is equal to 1,400 millimeters squared times 55 millimeters plus 1,000 millimeters squared times 10 millimeters, all divided by the sum of the area is 2,400 millimeters squared. So 1,000 times 10 divided by so y bar overall for that is 36.25 millimeters. So we're looking at what, right about here. Looks about right. I mean, obviously considering I didn't actually draw that to scale either. So what else? We've got our, we need to go ahead and use our parallel axis sim to figure out what our I is. So the I is just going to be equal to the sum of the I primes for each plus the area for each times its individual y bar squared. Now that's the y bar. That's the, when I say the y bar, that's the difference between this value and these values up here. So it's y bar relative to the centroid, not relative to that base that we originally set as kind of a convenient 0 point. So we'll start with the green. 1,400. Oh, start the I first, I guess. 571,666 millimeters to the fourth plus the area 1,400 millimeters squared times so that's 55 minus millimeters minus 36.25 millimeters squared. Now I did 55 minus 36.25 there, because that'll give us the positive displacement. Again, we're squaring it, so kind of the order in which you subtract there doesn't really matter. But strictly speaking, that would be the positive displacement from the centroid to the location of the centroid of the top of the green one. So for the other one, 3,300, 5 threes plus 10,000, sorry, no, 1,000 millimeters squared times, let's see here, 36.25 minus 10 millimeters squared. So let's see here. So that gives me a value of 1.79 times 10 to the 6 millimeters cubed. Okay, so we got our I now, and we got the location of our centroid relative to the bottom there. So now basically what we need to do is figure out what our maximum stress, shear stress is. And we know that the maximum shear stress will be occurring at the centroid, because that's the way shear stress works. So I'll just kind of try to draw straight lines. So we got 36.25 there on the top. That value would be 53.75, and those are both in millimeters. So I'm gonna go ahead and kind of repeat this calculation twice, just to demonstrate that it doesn't really matter which side we take that measurement from in order to find what the value is. But we'll start with the easy one. So, well, our shear stress, that is equal to V big Q over I T. So our V, that's equal to 6 kilonewtons. Yep, 6 kilonewtons. Our I, that's right there. Our T, across that cross section, 20 millimeters. So what we need to know here is the Q. Actually, well, you know what? I'm not going to demonstrate that. I'm going to say that we calculate that if our centroid is located here, then by definition, the centroid is located at a point where the area times the y bar y bar amounts is equal when taken on either side relative to that centroid. So that's that's the definition of where the centroid is. So we know that kind of on either side that that Q is going to be the same. So yeah, let's skip some tedious calculation just to prove that point. So our Q there. I guess yeah. Put that Q is equal to A times Y bar. So we're gonna, again, we can calculate it either for this red shaded section here, or we can calculate it for this green shaded section here, and this, oh, what did I do here? There we go. It's green shaded section here, and they'll be the same. So the easier one to calculate there is obviously the top part. So we'll stick with that. So area 20 millimeters times 53.75 millimeters times the Y bar, which will be 53.75 divided by 2 millimeters. So that there should be 28,890 millimeters to the third. So calculating our shear stress from there, that is going to be equal to 6,000 newtons times 28,890 millimeters cubed, all divided by 20 millimeters times 1.79 times 10 to the 6 millimeters to the fourth. So these millimeters here get canceled out, eliminating all but one of the millimeters on the millimeters to the fourth, leaving our overall units newtons per millimeter squared, which works out to megapascal. So 6,000 times 28890 divided by 20 times 0.79 E6. Oh. I got a result that was very obviously wrong, and I had punched in a times at one point instead of a dividing. So let's have a look there. There we go. That's far better. So the results of our maximum shear stress, that is going to be 4.84 megapascals. And yeah, that should be about that. So yeah, and that is, of course, so they gave it to us here, and they asked us for the maximum shear stress acting at that point, along this section. That'll be the same, along this entire span here, along this entire area where we've got the 6 kilonewton shear load. It's acting at the neutral axis. So if we're talking the maximum shear stress, it's acting at the neutral axis. So kind of regardless of where we are along the span, regardless of where our X location is, that doesn't change at all. And the bending stress the bending stress does change when you go sorry, I guess within the, it doesn't change at all within, not that span, but this span. The bending stress does, but the bending stress occurs, we get our maximum bending stress along the top here. It's not at the neutral axis down here. So essentially, kind of what's going on at the points where we're worried about the maximum shear stress, and what's going on at the points on the object where we're worried about the maximum bending stress aren't really, they're not acting in concert. They don't change the same way, and they're acting at different locations. So if we're worried about maximum shear stress, we're worried about what's happening in the middle. If we're worried about maximum bending stress, we're worried about what's happening at the ends. Which is why when we're doing these calculations for trying to figure out kind of like what the worst point is, we do those separately, and we don't really, we often kind of don't try to necessarily combine the two, because they're not acting at single points on the object.